start by thanking the organizers, both for organizing this workshop and also for giving me the opportunity to talk here. I also like to say that it's really nice to see all of you in person rather than seeing small pictures with faces on Zoom. And I hope this will stay open and have more conferences in person. So today I will discuss how to set up AdS CFT at loop order. Now, Juan said earlier today that we have been known how to calculate correlation functions forever. I think that's true, but it's mostly correlation functions at tree level. I think over the last, let's say, 5 to 10 years, we started to learn how to calculate at loop order. Has been a lot of interesting developments. But I think it's fair to say that the full set of rules on the bulk side has not really been understood. And I think the emphasis of this talk, of this work, is to set up the calculation tools, how to do AdS CFT to all orders. So I'll start this talk by briefly reviewing what we know at tree level and work from 20 years ago. Hopefully I'm going to say a few new things as well. And then we're going to move on to kind of generalize the discussion to loop order, and then at the very end I will specialize to a specific example, Phi-fourth theory in fixed AdS background, but I hope it will be clear from the discussion that pretty much everything I'm going to say holds completely generally. Okay, so let's start from the beginning, AdS CFT at tree level. Well, the rules of the correspondence have pretty much understood almost from the word go. So shortly after Juan's paper, there was the two famous papers, the Kupsa-Klebanov-Polyakov and Witten's paper that set out the main framework of how to do calculations. So essentially, at tree level, what one needs to do is one needs to calculate the on-shell value of the action as a function of the fields that parameterize the boundary conditions for bulk fields, and then use these fields as sources for the dual operators. Now, of course, I mean that works, but that almost immediately raises an additional issue, namely the on-shell value of the action diverges because essentially from the infinite volume of space-time. But quite remarkably, it turned out shortly afterwards, I mean essentially in this paper, that these infrared divergences are all local. And therefore, one can use the technology that we know how to normalize, so from standard quantum field theory, in order to set up an analog of normalization, which was coined holographic normalization. And once you do that, then the rest is basically following your nose. So there are well-defined rules how to obtain renormalized conformal field theory correlators, and more generally, you can start then deforming the CFT to get the general quantum field theory, and again, you know how to calculate correlators in that context. Okay, now let me make a couple of comments. First of all, I think that already has kind of one big message, the one I put over here. So already from what I said, we get a very strong indication that the bulk is a local quantum field theory. I mean, the trademark property of local quantum field theories is that its UV divergences are local. And another main point for gauge gravity duality is there is a so-called UV-IR connection, which was also understood very early on in the game, namely UV properties of the boundary theory are linked to infrared properties of the bulk and vice versa, and I will use that also in a minute. So this means that if you want to understand properties that we usually understand through renormalization on the quantum field theory side, like for instance how symmetries, the implications of symmetries, the Ward identities, and how the symmetries may be broken by quantum effects, namely the anomalies, all of these things can be established without actually needing to do a complete computation. You only need to look at the infrared properties of the bulk, and it turns out to be the case. One can fully establish Ward identities and anomalies by analyzing properties near the boundary. So this type of arguments suggests that this give us a very strong structural evidence for AdS-CFT correspondence. I think here I speak to the converted. I think we all believe AdS-CFT is true, but when one speaks to audience from different communities, quite often one hears questions like, is this correspondence true because of symmetries, because you look for n equals 4 Spigag-Mills that has so many supersymmetries, or is there something more? And I would say this type of argument shows that there is not the correspondence is not an accident of a very symmetric point. There is structural evidence for the correspondence. The bulk theory has the analytic structure to be a d-dimensional local quantum field theory. So the purpose of this work is to generalize these results now to all orders in loops. And part of this work started because there have been many interesting results over the last 10 years or so where people started mostly on the CFT side, and they did a computation that would imply loop corrections on the bulk side. And here I listed a number of names, and I'm sure I forget many, so I apologize if I didn't put your name up there. So our aim is here to kind of go to the bulk. So all of this talk is going to concentrate on the bulk and present a systematic normalization procedure that deals both with UV and IR issues. And I want to emphasize that one really needs to kind of deal at the same time both with a UV and IR issues. It's not sufficient to just look on one or the other. And in some of the previous works, people either concentrated, or most of them mostly concentrated on UV issues. So this talk is based on a collaboration, an ongoing collaboration with Max Bagnados, Ernesto Bianchi was his master student, now my PhD student. Ivan is Max's student, and he will be applying for postdoc positions. So keep an eye for him. So I think it's going to be a series of papers that will appear. The first one hopefully will appear in the next month or two. We're almost finished, but it is summer and then conference period. Now, before I move on to discuss how to set it up, the normalization, I also want to make another general comment. Another question that one often gets is holography a property of gravity, or do you need string theory? And I want to argue that by just thinking about this type of issues, we also get that the bulk is a string theory. Now, I mentioned earlier there's a UV-IR connection. So UV properties of one theory correspond to IR of the other, and vice versa. And previously, I used the properties of the quantum field theory in the UV and look at the corresponding properties of gravity in the IR to argue that it's a local quantum field theory. But we can look on the other way around. So we know that infrared divergences in quantum field theory have to cancel on their own. We do not add counter terms to cancel infrared divergences. So the theories have to be finite on its own. And so it should not be normalizable, it should be finite. And the only finite theory of gravity that we know is string theory, so it should be a string theory. Of course, in actual computations, this we do at low energies with some supergravity Lagrangian. So we have some gravity theory coupled to matter. So this should be viewed as an effective field theory. And in that context, of course, the loop diagrams in the bulk on the gravity level do have infrared divergences and need to be normalized. And when you do this, and I will again go back to that later on, every time you normalize, there's always scheme dependence. And scheme dependence is resolved by thinking of the theory in the UV. And it will be similarly here. So the finiteness of the gravity theory, the string theory, let's say the specific coefficient, for instance, of the R to the 4 term, fixes specific scheme dependence when you do the loop computations. So the loop diagrams also have bulk infrared divergences. They do not just have bulk UV divergences. And these need to be treated with holographic normalization, as it was done for the tree-level diagrams. And there is an interplay between the two, and as I will mention as we move on. Okay, so this was my brief overview of AdS-CFT at tree level. So next, I will discuss how to move on to loop level. Okay. So I will start by putting the general setup, the formula. Also, some people often say, well, there is a big advance in physics, there is a new formula. Like, it's with fermions with the Dirac equation. What is the new formula for AdS CFT? I would say this is the new formula for AdS CFT, the formula that defines the correspondence between the two sides. So on the left, we have the bulk. And here I will denote collectively with phi naught the boundary, the fields that parameterize boundary conditions. And on the other side, the same quantity acts as a source for a gauge invariant operator of the CFT. Now on the left, we also have a number of parameters. That could be the masses of the fields, the coupling constants, and so on. And on the left, we also have a set of parameters, which are the parameters that parameterize the CFT spectrum, the OPE coefficients, and so on. So to have an equality of this type, we need to have a map between the two parameters, which is 1 to 1. And I already, in a sense, giving you 1, so the phi naught appears exactly in the same way. And we know how these parameters map to those, again, at tree-level computations, but we'd like to understand that to all orders. Okay, so now what is renormalization in this context? So first, we need to regularize. So we need both a UV regulator, which I would call tau, and an infrared regulator, which I would call epsilon. So again, all the discussion now is going to be on the bulk side. So for everything that appears as argument here, all of these quantities need to be normalized. So then I'm going to introduce a z factor for all of them. So this is the bare quantity, and that's the normalized quantity. So here I put different color for this one, because that's sort of the analog of wave function normalization in standard quantum field theory. But in this context, this is really a boundary coupling. So it's a field that parameterizes boundary condition. It's not wave function normalization. And we would say that the theory is renormalized if one can find z factors and a boundary counterterm action such that this regularized quantity has a limit. So this would depend explicitly on the two regulators, and then it would depend on the z factors through the bare couplings. And then we want to have the z factor such that all the epsilons and tau cancel out, and we're left with something which is finite. The normalized correlators would be obtained by differentiating with respect to the source var phi. Now, I do want to emphasize again, and because that's a point which I think at least partly was missed in the literature, the kind of the one-loop literature so far, that every time you normalize, there is a scheme dependence. It's very important to keep track of it. And to fix scheme dependence, we need renormalization conditions. So that's an integral part of renormalizing. Okay, so that's the general prescription. So now I'm start unpacking it a little bit. So what are the regulators? Well, the infrared regulator is the usual one we already used at tree level. So if I write AdS in these coordinates, I will cut off the radial integrals at some point epsilon. Now, what about the UV regulator? Now, again, thinking about AdS CFT, we know on the CFT side that infrared issues do not further break conformal invariance. So this means there must exist an AdS invariant UV regulator. So our first task is to find that regulator. And there was already a couple of very interesting papers from 2018, which was an inspiration for what we did here. But essentially, this AdS invariant point splitting, this AdS invariant regulator is an AdS invariant point splitting. Now, suppose you have 2 points x and y in AdS. I will call xi the coordinate distance. And now, in this coordinate, if the points are coincident, then xi is equal to 1. And now, given these 2 points, I will consider a very specific geodesic given over here. So sine x naught is the radial direction, and the vector x is along the boundary. So we pick a unit normal to the distance x and y, and then we consider the following geodesic, and we go out distance tau. Now this has a very remarkable property, namely if you now compute the chordal distance between this x of tau and y, then the answer is given over here. So the only thing that happened was that we rescaled this chordal distance by a function that depends on tau. So this means, first of all, this is automatically says that this is an AdS invariant regulator, because everything is going to depend on this psi tau, and this is an AdS invariant distance. And secondly, it only regulates all UV infinities, because this quantity here is never equal to 1 if tau is different than 0. And again, this was inspired by this paper. In that paper, what they did is they used the idea that you can scale psi in order to get to regulate the quantities, which is indeed what happens when you kind of set up the system in this way. So then you have the regulated bulk-to-bulk propagator, so you take the usual propagator, and then you just move that point to x of tau, and namely the bulk-to-bulk propagator now is going to depend on this regulated quantity. And if you do this, this is sufficient in order to regulate all UV infinities. Okay, so now let's go back to kind of a bit more general comments. I mean, we know that conformal invariance fixes 2- and 3-point functions up to constants, and we also know that high-point functions are again fixed up to functions of cross ratios. And to find out about this, we do not need to do any explicit computation in any specific model. That this just follows from symmetries. So since we're able to regulate the bulk UV divergences in a way that preserves the AdS isometries, this means that we should be able to establish exactly the same results without having to do any computation. And indeed, we're going to see this is indeed the case. One can establish these results just on using the general structure I developed. Now, in CFT, we also know that conformal correlators do need to be normalized, because gauge invariant operators are composite operators, they're additional infinities because of that. And we also know that if you have a perturbative system, then you can develop anomalous dimensions. And both of these issues would be related to infrared divergences in the bulk, not UV divergences in the bulk. Again, we have this UV-IR connection, and we know that on the CFT side, you get anomalous dimensions, and you need normalization because of UV issues in the boundary theory. This means this should be mapped to infrared issues in the bulk. And we will see that that's the case indeed. Okay, so now this is the general setup. So now I'm going to illustrate this using, as an example, the Phi-fourth theory. Okay, so now in this context, I have fixed AdS background. This will be my Lagrangian. So what I called earlier P naught I, it's the masses and the coupling. Now to do the computation, I will split the bulk field into a classical part and a quantum fluctuation. Now the classical field is going to tell me the boundary conditions. So I will start having directly boundary conditions. So the phi naught that I had in my previous slides is the leading term in the near boundary expansion of the field, like in the standard discussion in holographic normalization. And then we need to integrate the quantum fluctuations. Now the quantum fluctuations vanish at infinity because we already take care of the boundary conditions through the classical field phi. So now the regulator theory here is defined by doing a path integral over h, and we have this prefactor, which is the on-shell value of the action, regularized the way I just described, plus the boundary counter terms. Now at tree level, everything comes from here. So you can derive the form of weighting diagrams and so on, all of them properly regulated by using this term. Now the main task is to take the contributions from the path integral over H. Okay, so now let's go through one example, kind of the one which has been actually appeared in many papers. So let's do a tadpole diagram. So this is the boundary of AdS. So these lines here are back-to-boundary propagators. So we need two of them. These terms over here, and then we have this bulk-to-bulk propagator which go back to itself. And because it goes back to itself, and psi at constant points is 1, then this part goes outside to the integral, and we get this expression. Now, this expression, if you take the limit as tau go to 0, then you can see that you did get an infinity. But then one can show, but by just changing variables in this integral, which amount to conformal transformations, one can arrange so that all the y dependence from here is moving outside the integral and takes exactly the expected form. So it takes the form of a two-point function with dimension delta, with some specific prefactor, which comes from here, and some numerical constant, which is doing the remaining integral. Now that actually generalizes to all orders. So if you have, again, a correction to the two-point function, you have a kernel here that contains bulk-to-bulk propagators and so on. So I can run exactly the same argument, doing the same change of variables. So this all depends on the quantities having well-defined transformations on the conformal transformations, and then the answer is the same. Now that constant over here, which depends on the regulator, is infinite. It can be removed by just renormalizing the source, because it's just multiplicative. So from these arguments, this would suggest there are no anomalous dimensions, which of course we know is not the case. So we're missing something. And what we're missing is that we have forgotten that these integrals have infrared divergences. So if you actually put the infrared cutoff, then that integral here takes a kind of more complicated form, has now infrared divergences, and now one says that in order to remove infinities, you must add a mass counter term, and that induces an anomalous dimension, plus you need to normalize the source. So I'm in the final 5 minutes, so I have to speed up a little bit. So for high point functions, the discussion is similar. If one ignores the infrared divergences, one can use the same argument to show that you recover the expected form. But because of infrared divergences, you find that there is a need for anomalous dimension, which confirms what we already learned from the two-point function. And then the remaining bulk UV divergences can be removed by normalizing the mass and the bulk coupling. So I have explicitly carried out this to up to 4-point functions up to the order lambda square. It turns out that this specific theory is normalizable up to 6 dimensions, meaning there is no new couplings required. The fact that it goes up to d equals 6 is perhaps slightly surprising. If you are above 6 dimensions, then you need additional terms of that form. And just a slide of how these things look like. For one specific case, we've done any delta and any m, any dimension. So I'm just going to focus in AdS4, delta equals 2. Then this is the z factor for the coupling constant. There is a beta function for the coupling, which is this one, is exactly the same as in flat space in 4 dimensions. That's not unexpected, because short distance distances should not care about the long distance asymptotics. Then there is a normalization of the mass. These are the infinite terms here, and then these are the finite terms. And here I want to emphasize the scheme dependence. So the functions S1 to S4 are functions that encode the scheme dependent arbitrary functions. And the anomalous dimension is already scheme dependent at leading order. So without specifying the scheme, you cannot say what is the anomalous dimension. So the results are completely consistent with conformal invariance to all orders. And again, scheme dependence affects the values of delta, lambda, and the normalization of the dual operator. So for that, we need additional UV input, and that can be either the spectrum and interactions in string theory in AdS, or equivalently using the same information in dual CFT, and I'm finishing. And this is the result for 4-point function. So all the scheme dependence is now hidden inside the delta. So this delta is 2 plus the anomalous dimension. The one piece here, that's the 3-level one, and all other ones can be re-expressed in terms of the D function. So at the end, the original expression is complicated, but could be resummed to a fairly simple form. Okay, so since I'm out of time, let me just very briefly summarize. So what I discussed in this talk is how to set up bulk normalization in the AdS CFT. Bulk normalization is completely consistent with what one may have anticipated from AdS CFT. I believe this also provides further structural support to the duality. This is not something which comes because we have some very specific symmetric theory. Of course, there are lots of things still to be done. I mean, I think almost everything that I said is held in complete generality, but it would be nice to do them very explicitly, like discuss graviton exchanges, work out all loop formulas for general endpoint functions, and of course connect back to the discussions from the conformal bootstrap, which was part of the motivation for this talk. Thank you very much for your attention.
Questions?
Hi. Is there any room for such loop expressions to break conformal invariance, or is it guaranteed to be preserved to all orders?
I think there's no more breaking than what we know from conformal anomalies. And then everything else is consistent with conformal invariance. And you can show by the same argument, because you can start from the diagrams and arrange so that all the space-time dependence of the external legs are pulled outside of the integral. And then you can check what is left inside is precisely expressed in terms of cross ratios. So there's no further breaking. Of course, if there would be further breaking, it would contradict AdS CFT the way we understand it.
Hi, Kostas. I'm here. Here.
Yeah. Yes.
Hi. Yeah, thanks for the nice talk. I have a question about the last one slide. So, as I understand, your program is to do an effective field theory in a curved space background, really. And there's still this additional UV information, like is there a connection to 1/n corrections?
No, all of these are 1/n. So one loop is 1/n squared correction. So two loops will be 1/n squared, and so on. So all of them are 1/n squared corrections.
So, and do you have the input from the string?
We do have right now, actually, most of these things, it could have been done 20 years ago. But at the time, I thought, the chance of calculating this on the CFT side is more to zero. But right now, the last 10 years, people through the conformal bootstrap have calculated many of these quantities, and I think that this was a huge motivation for me to go back. Now with this, I believe now it's a completely systematic framework, and we start connecting CFT and bulk and fix all of the scheme dependence.
Okay, thanks.
I think Kumaran also have one. Yeah.
Thanks for the nice talk. So, as you say, the bulk could be viewed as a stringy computation ultimately, and the UV divergences of string are, we know they get tempered by the conformal symmetries and all that. So at one loop, we have this SL2Z, which is the UV-IR mixture in string mode. So we have a bulk UV-IR mixture, which has to be taken into account. Have you encountered computation where that's crucial for it, and how would it be reflected in this AdS CFT context?
I think to some extent what we see here, that's a UV-IR connection. So without the IR divergences, you wouldn't see the anomalous dimension. So you need both the UV divergences and the IR to actually see the actual effect. Without the one, there wouldn't be an anomalous dimension.
So do you see a computation which is crucial to restrict the fundamental domain of the torus?
Yes, Well, I mean, of course, here I've done everything at the supergravity level. But I see on the supergravity computation, there is a connection between the UV infinities and the IR infinities. If I wouldn't have both, I wouldn't get a consistent story. Okay. But we can discuss more afterwards,
Okay,
yes.
We're out of time, so maybe we should end the class.